CLI and a cross-platform IDE for C and C++. Download now.
Welcome everybody to my talk, Fast and Small C++ when efficiency matters. Quick words about me. I offer in-house training on-site or remote, whatever works best for you. Just feel free to contact me. I also have self-study options if you want to prefer learning at your own pace. I'm German. My last name is a very typical German name. It's Fertig. And I'm known for pronouncing it wrong myself. I tried hard to do it right this time because usually I say Fertig with a hard K in the end, and that's not proper German. You can translate it to English as finished, ready, complete, or completed. So I can say it's a real nice name, right? It has a finishing touch, so a positive thing. I think that's great. But I'm not here to talk about German lessons. We are here talking about C++, right? And this talk today, I worked a long time in the embedded domain. I like the bit fiddling stuff. I did a lot of networking there. I'm always working in constrained environments, systems that, were under some regulations. And so I tried to pick up patterns and tried to learn how to write efficient code for them. And that code had also to be safe at the same time. And this talk now showcases a couple of the things that I picked up, I learned, and that you also can find in, let's say, the standard library. So this is a source to learn from as well. I often look into the standard library, checking out how they are doing things. So let's get started. The first thing I have here is a compressed pair. And what you're seeing on the screen is not really a compressed pair. What you're seeing on the screen is a data type that you potentially know it's a unique pointer from the standard library. And here I'm showing a slightly different version. I would say a less frequently used version, at least for the code I see. This is a unique pointer with a custom deleter. So a unique pointer is a really great um, thing to manage pointers in a smart way. So have their destruction in a control, have the ownership control. This version of a unique pointer now allows me to control not just the regularly allocated pointers with new that need to be freed with delete. This version here allows me to supply a custom deleter. And that means I can teach my unique pointer to handle a resource that's working different to the traditional way. And the example I have here on the slide is using a POSIX fopen, which returns, when opening a file, incidentally, a file object. So sorry for the bad naming here, but the data structure that's returned is file in capital letters. And what we opened with fopen, we must close with fclose. So behind the scenes, there is resource management going on. So obviously we have to open the file, we have to allocate memory for this data structure file, and then we have to give this back to the operating system at the end, which we are doing by saying fclose. The unique pointer that you see here now, I've taught it to do that. So I use it together with fopen, but then I supply two parameters to the unique pointer's type. Instead of just having the regular type of the pointer that the unique pointer is wrapping file, I supply a second template parameter. This is decal type of fclose. Why? Because I always forget how the exact signature of fclose looks like. This is why I have the decal type here. You could also write out or spell out the entire function pointer signature that matches the fclose call. When creating the unique pointer itself, then I also have to supply two parameters there, the result of fopen, of course, and the pointer, the function pointer to fclose. This function then gets invoked instead of delete when the unique pointer goes out of scope. So it's a cool thing, really helpful, another way of using a unique pointer that also makes it possible to use unique pointers in a lot of embedded scenarios where you have different ways of dealing with new and delete. Unique pointer, usually we say it's a efficient thing, it's a great replacement for a raw pointer, and I totally support it, that's true. If you look at this specific version here now and ask ourselves, how efficient is it? And efficient in terms of memory consumption. What we want from such a thin wrapper is that its file size, or sorry, its total memory size is equal to a file pointer, so 2 pointer on my system. Is that true? Let's check it out. So if I squeeze in a static assert here that asserts that the size of my f, is larger than the size of a void star. So size of f is greater than size of void star. And that static assert here passes. In fact, on my machine, the correct comparison here would be comparing the size of f to 2 times the size of void. Because we are passing 2 pointers, right? So it's reasonable. Pointer of f open, that's what a unique pointer usually encapsulates, and the pointer to the function pointer of f close. So this unique pointer needs to store 2 pointers, ergo the size of 2 pointers. Might be all right if my f close would really change during runtime, but it doesn't. It's the same all the time. The linker already knows the address of f close. It's hard in the binary. It never changes. So the question here is, do I really want to pay for this extra pointer? And I don't know about you, but I don't want to pay extra for this f close here. So what can we do? Or better, what does the standard library do to help us out here? The standard library uses a optimization technique that we have, I think, since the beginning of C++, and it is called EBO, the empty base class optimization. EBO roughly means that if I have a base class, as I presented here on the screen, that comes with no non-static data members. So base here does not have any data members, it just has a single function. So a member function designed inside base. The size of base itself, if we ask it with the size of, is 1. Despite that it's free of any non-static data members, the size is 1. Because if we want to ask for the size, the system accounts for the fact that we might want to take the address of such an object, and to be addressable, it requires to have the size of at least 1. So even an empty data structure, if you ask for it, has the size of 1. If I now use this empty base class and derive from it with my class derived here, and derived has a data member, it's a uint32t and data to be precise about the width at this point. If in use now I declare such a derived object and I assert whether the size of d is equivalent to the size of a uint32t, that static assert passes. This time the base class does not contribute its size because its size is 0. So this is a way how we can have a base class with a member function. That one is empty. If we ask for the size, we get 1, but its real size is 0. And we can leverage that. If we derive from it, then its size remains 0. We can still, as I show in line 17, of course, since it's inheritance, call member functions on the derived object from the base class. So I can invoke fun here from the base class. And this is key for what the standard library does. In pre-C++20 code, this is what they implement. In C++20, we will see that later, they have a couple of other options in their sleeves. So this is still not a compressed pair, right? What the standard library does is for the unique pointer, they always take 2 template parameters. The type of the pointer you want to store in there, and a second pointer, the so-called custom deleter. And here you see the implementation of a default deleter called default delete. It's once again a template, and internally all it comes with is a call operator, taking a t star and deleting the PTR value that I pass in with this pointer. So every unique pointer you create has this default delete in it, which then invokes the standard delete. The unique pointer itself, if you look at its implementation, it comes with the two template parameters that I just explained. It has the second one defaulted, initialized with default delete of t. So if we don't supply anything, that one will be the one that's active. And then I have the data structure compressed pair in A here. That one is typed with the deleter and my t star. I call it in pair here. The standard library might call it differently. We have a constructor here with a single argument in my unique pointer. That one initializes Ampere by passing just a pointer value. And then I have a two argument constructor that passes a t star and the deleter to Ampere. You know the drill, a unique pointer is only movable, not copyable. So the copy operations are deleted, move operations are implemented. And if you then put your eyes down to D, then you can see in the D structure there, now we use this pair. We have this check whether the pointer that we stored in Ampere is a null pointer, then we don't do anything. But if not, we invoke the deleter that's stored in Ampere with the pointer that's stored in Ampere. The reason for that looking like this is the compressed pair is used in other places in the standard library. So it's a general utility type. I renamed the members here. Usually they refer to it as first and second, like a true pair. But I thought it made more sense to have the more meaningful names for this talk in here. So the implementation of compressed pair in C++20 looks like this. I'm not using EBO technically, so the empty base class optimization, because I have C++20. The code would be way larger if I implement that in C++17 or before. Way more lines of code, way uglier to read and to get the gist from. In C++20, I can use the new attribute no unique address. And that one works the same way as EBO. Should that data type have the technical size of 0, then it does not occupy any storage space in this data structure. And this is what we leverage here, because my deleter and my pointer for completeness are flagged with the no unique address attribute. That means if my deleter that comes in is a class type with no non-static data members, then it does not occupy any storage space in there. But I still can call the member functions. I still can call a potential call operator on this member deleter here. So this is the trick. And if I now use that and apply it to my own code, I can say, okay, I have these beautiful 3 lines here. It's C++20. I really like them as they're such a great utility. I have this templated using alias here. I call it unique pointer deleter. It takes a type name t and a C++17 non-type template parameter auto. Call that one delete fn. So that's later my function pointer signature. I'll let the using alias point to the unique pointer of t. And the second parameter to this unique pointer is a decal type on a captureless lambda. That's cool. In C++20, we can have captureless lambdas in unevaluated context, and decal type is one of them. So my captureless lambda here, it takes a t star because we are in a template context anyway, and it invokes delete fn on the parameter it receives. So this is my empty base class, because lambdas are classes behind the scenes, right? So this is what we are doing here. And then I have my unique pointer deleter in line number 5. I use it. And from the using perspective, it's also really great. I provide the data type I want to wrap file and the function I want that thing to invoke when the unique pointer gets destroyed, fclose. And that's it. The rest of a unique pointer looks like a regular one because I have to supply only one parameter to the constructor. So no repetition there, no unintentional mix-ups. And the best thing is if you're checking the size now, that one compares equal to the size of a single void star. So I trimmed this data structure's size by 50%. That's a really great thing, and that's something that you can translate to your own code base. Of course, if you're using a unique pointer with custom deleter, you should think about applying this technique here. But if you have own data types that do similar things, maybe this one here helps you as well. Looks already good, right? Can we do any better? Maybe not. Maybe. If we are using C++23, in C++23, we have two operators now that can be static. The array index operator, which is irrelevant for that part, and also the call operator. So these two operators can be static member functions in C++23. And since the call operator can be static, it can be so for a lambda as well. So I can have the lambda with a static call operator. Because let's face it, in a captureless lambda, I never need the dis pointer because it's captureless. There are no data members in it. So I don't need a dis pointer. So making the call operator here static saves you around 1 to 3 assembly instructions. So this is if you're really in for the maximum optimization, you might look into C++23 and tune your lambdas there a little more. What else do we have? Well, remaining in the standard library, std_string. It's such a great data structure. Nearly every of my customers has an own implementation of a std_string. So it's worth looking into how the standard library does things and how clever they are. And for the std_string, you might already have heard of that. It comes with a so-called small string optimization, SSO. And that is because someone decided that there is a threshold until or before it doesn't make sense to allocate memory dynamically because it's too expensive to do it. So the common threshold is to say around 16 characters. Everything below that, we don't allocate dynamic memory. We use a little buffer that's stored inside the std_string itself. So it comes with a little extra space, the SSO buffer. And the goal is now to look into the different implementations of the standard libraries and see how they are doing things. Here is a sketch of an implementation that we could do to store all the information. So this is what we usually need. We need a size. So what is the number of characters that's currently stored in the std_string object? Capacity. So how much dynamic memory did we allocate? So what is the maximum number of characters we can currently store in the std_string? Of course, it can reallocate. The pointer to the data makes sense. And then the SSO buffer. In my case, I use 16, so that's usually the number the standard libraries use. And because I can now have two modes, a small string and a long string mode, I need a Boolean to know in which mode I am, right? That's a rough implementation. If I check that one on my 64-bit architecture, it has 48 bytes in total. Well, C++ Insights can shed some light on what this is here. So we have the transformation enabled show padding information. And if I transform the code here, then you all can see that we have at the very end of this data structure 7 bytes of padding. Because the data structure itself, as C++ Insights shows here, has an alignment of 8. And by adding this Boolean, I just exceeded that current size by 1. And so we need to add 7 more bytes. And where I worked, 7 more bytes in a data structure like that, that was kind of a lot. So we didn't want that. But this is just my simple implementation, right? So let's see what the standard libraries can do here for us in this case, because they are truly more clever than I am, and they have way more experience doing that. So what I'm going to do now is I'm showing you the different implementations of 3 major standard libraries. So GCC, Clang, and MSVC. They're all modified in one part, and this is that I want them to consume no more than 24 bytes in total to make them comparable. That means for some of them, the small string capacity is in the implementation I'm showing you lower than its actual real world is. So please keep that one in mind. And there might be other things. A lot of the stuff is left out, but we want to look at the data structure and the layout here. So the first implementation we have is libs.c++. That one starts by storing a car star and pointer, followed by a size t and size. And now the trick starts to come into play. They have a union in their string, and that union stores either a capacity of type size t or a car array of size 8. So 8 characters. This is where I said in reality it's 16, but I did shrink it to 8 here to make that overall data structure, as you can see it in line number 9, fit into 24 bytes. Then we have a couple of utility functions that will be the same for all the implementations. Max capacity tells us what's the theoretical or practical maximum number of characters I can ever store in this string. And that would be the numeric limits of a size t's maximum. So whatever your size t on your architecture is. SSO capacity here is the size of mbuff minus 1 because we have to store the null terminator. So that would mean 7 characters, small string buffer. That's not a lot. Fits into SSO simply checks whether the length is less than or equal to the SSO capacity. And the rest of this trick part is now in isLong, because what they are doing there is comparing whether m pointer, so the pointer of your data in your string, points to the address of mbuff. So is the address of m pointer not equal to mbuff? That means it points somewhere to dynamic memory. So we are in long string mode. And if the addresses of the two compare equal, we will be in short string mode because m pointer would point to mbuff. This is exactly what a constructor in line number 17 implements. So the one argument construct or the default constructor always constructs a small string, and the two argument constructor taking a pointer to the data and its length also starts out constructing a small string buffer, but it checks for m pointer. Does the length fit into SSO? If yes, m pointer is initialized with mbuff. Otherwise, we allocate data from the heap. We set size. We initialize mbuff in my union. So this is my current active member. And then in the constructor's body, we check whether we are in long string mode. And if that's the case, we make mCapacity the active member by setting the length. Then, of course, we would carry the data, so giving that string real life and meaning. Size and data are direct access, so they simply return us the data members that are stored inside the string. And capacity now comes with a branch. Capacity has to check whether it's in long string mode, then we return mCapacity, or it's in small string mode, then we return SSO capacity. So this is the implementation of GCC. And I would say that's real clever, right? They managed to squeeze that single Boolean that I foolishly put into my implementation into a better data structure because they know they need either mCapacity or mbuff, but never the two at the same time. So next implementation is MSVC standard library. And this is a little like the GCC implementation. They start with a union and they put a car pointer and PTR in this union and a 8-byte car buffer. So they decided that they either need a pointer to the dynamic data or the stack buffer, but never the two at the same time. Followed by that, they have mSize and mCapacity, as previously GCC showed as well, or libs.c++ to be precise. The total capacity here, once again, 24 bytes, so the same as GCC. We have the same limitations, so max capacity is the maximum of a size t on your architecture. SSO capacity is mbuff -1, means 7 bytes here, so exactly the same as GCC. And isLong now does a different way of the trick. In isLong, they are checking whether the max capacity exceeds the SSO capacity. So this is how they distinguish between the two modes. So not putting it into Boolean. How wrong was I? Default constructor constructs a small string by default, and the two-argument constructor makes mbuff, the active member in the union, set size, and for capacity now it checks whether the string would fit into SSO, and if so, mCapacity is simply set to the SSO capacity and otherwise to the actual length of the string. In the constructor's body, there's another check whether we are in SSO mode or not. So in long mode, we allocate dynamic memory for the actual string, and then we copy the data over into whatever it then is, our local buffer or the dynamic one. The nice thing is they still have two member functions. They come branch free. Size and capacity have in this implementation no branch. They directly return the data members. And data now has the branch. That one has to check whether it's in long mode, then return mptr. And if you are in short string mode, we return mbuff. The question is, where do you want to take this hit? One of them has in some way to be the one with the branch, and don't ask me why they decided differently or why GCC decided differently, but this is where you can adjust your fine control. If you say that data is the function that's hot and that has to be branch free, then the GCC libstood C++ implementation would be the better one. Otherwise, go to the Microsoft version. But we have a third one. And that one comes from libc++. This is the standard library that Clang comes with, at least on macOS. On Linux, you can also use it, but it defaults to libstood C++ if you don't do anything. And this is also the newest among all of them. And by quickly looking at this slide, you can tell it's a lot different. So this is the first implementation that I was no longer able to squeeze on one slide, at least not in a way that you can still read the code. Their std_string implementation does the following. They have two different data structures inside their std_string. One is called normal, the other one is called SSO. Normal starts with I like that, with a single bit field bit large of type size t, followed by a size t bit field capacity, and that one has the number of bits of a size t -1 because we just spent one large. Followed by a size t for size, followed by a char star data. SSO, the structure SSO, also starts with a single bit field of type uint8t. It's called large, followed by another uint8t size. It's a bit field of the number of bits that the uint8 has -1 because we just spend one for the large bit. Then there comes some padding in C here. The padding is whatever is required to make the two previous data members align to a size t in total. So uint8t minus a size t. So we're wasting a couple of bytes here. Followed by a char array data, and that one has now the size of normal minus the size of a size t. That means this field here has 16 bytes. That's cool. If you want to optimize for maximum number of small string mode, that's a great way. They play an equivalent trick as the others did. They have a union here, store small and large in them, and the static assert here should support proof. Still, everything fits into 24 bytes. But now let's look in how they use it. So max capacity now, that one is slower than in the other two implementations. It's power of 2 of the bit capacity because we used 1 bit, so it's not the full width of a size t. SSO capacity, on the other hand, that one is quite interesting because it's the size of SSO's data -1. So 16 -1, that means 15 bytes of small string space that you have there. So that's twice more than the others had, right? So this is great for that. Is long? Well, that one checks in the packed union for the small member whether the large bit is set or not. By default, it constructs a small string with the union here, the 2-argument constructor taking a const star and a size t also default constructs a small string. And then we have the if inside the constructor body checking whether the length of the string fits into SSO mode. If yes, then we set the size in our small data structure to len. Otherwise, we flip the bit in the large structure. We set a large bit to true, and we set the size there to len as well. That would be followed by allocating potentially the data that's required for the dynamic version and copy all the data into the local buffer. The drawback from this implementation, I mean, we have the large SSO buffer is with a branch for each access. Whether it's size, data, or capacity, we have to check the bit and return the correct data member here. So that's the not so good part about this implementation. But once again, pick what's the best for you, right? If you can afford that and want a large amount of small string buffer, and that's a great implementation. Now the question is, can we do better? If you pause for a moment and think about what would be the maximum that we couldn't squeeze out here. I mean, we don't have the time. If you rewatch this video later, maybe you want to pause at this point and give it a thought. So we say we have 24 bytes in total. So this is our maximum. And you now saw 3 implementations doing that plus my beginner's implementation. So what is the maximum of characters we would be able to store in this small string buffer if we want to optimize for a large as possible small string without spending more than 24 bytes? Do you have a number? Do you have a rough implementation in your head? I have a 4th implementation for you. This is from Facebook's FB string. And as far as I know, it was at least started and written by Andreas Fertig, and it's brilliant. I'm not sure whether it's inspired by lit cplus's implementation or whether that one was the first. It looks a little similar to them. So they also have 2 data structures. They have one size and one SSO. One normal and one SSO. Normal here starts with a car star data, followed by a size t size, followed by a size t capacity. The last one here is set to be virtually reduced by 1 byte. So that's relevant later on. The struct SSO has a single data member, and that's a car array data with the full size of normal. So assuming we are still going for 24 bytes, that means data in SSO is 24 bytes. Oh, that's awesome. We put the 2 in a union, name them small and large. We assert everything has 24 bytes in total. Perfect. Max capacity here is a little different. We have the power of 2 of the size of capacity here. So the size of a size t minus 1 byte, right? So it's a little less than the others, or a lot less if you want. SSO capacity, on the other hand, and this is where things get interesting. It's the size of SSO minus 1. So 23 bytes. How the heck do they manage to store 23 bytes of payload in this small string? They have this getModeByte function. And getModeByte here, as you can see it, returns you from mdata's array the most significant byte. And it returns it either as value or as reference. And isLong now fetches this byte, so-called mode byte, and compares it to 0x for 0. So it checks whether the 7th bit in a byte is set. Why the 7th? Because the original or the full Facebook implementation of FB string has not only a short and a long string mode, they also have a middle string mode. And middle string would then be the 8th byte. So we have the 7th here. Oh, and by the way, it's not too late now, but Nicholas Omrod gave a great talk about this implementation. It's a 30-minute talk at CPBCon 2016. So I will spoiler, or I already have spoiled a couple of things he says in his talk. And it's a brilliant talk. So either watch it now or watch it later. I'd prefer if you stay, of course, but it's up to your choice. All right, now we have this mode byte. And how is that used? As all other implementations, default construction constructs a small string. Everything other would be insensible. My constcar star and size t version also starts constructing a small string, but then they are checking whether it fits into SSO. And if it fits into SSO, they set the mode byte to SSO capacity minus length. So what that means is they're not storing the number of characters that are currently stored in this string, as all other implementations did. They're storing the number of remaining characters in the string. So this number here that's stored there will go down to 0. And this is the last byte in our car array, in our 24-byte car array, right? And if there is no more space for a small string, the last byte is 0. And 0 is the null terminator. So this, my friends, is how you really pack a lot of information in 1 byte and pack your data structure to the maximum. So they take the same hits as libc++'s implementation. Everything comes with a branch here, whether size, capacity, or data, but they squeeze a heck of a lot of bytes into this 24 bytes. So this is the best you can get when it comes to optimizing for the small string buffer. All right, enough about the small string buffer. Let's look at something different. Const expressions. I teach for a living now. I teach a lot of C++ classes, and something I always had a hard time teaching is Constexpr, right? It's hard for some people to grasp how cool Constexpr is, where it helps, and where to sprinkle it in. And it's not just in the training classes. When I do consulting, it's the same. And I brought today a real-world example, and I hope this helps everybody now to understand the powers of Constexpr better than ever before. So the customer came and told me, of course, they were quickly before the release, shortly before the release, they were running out of RAM. So they wanted me to do something about that. And I looked into that. I figured out the device was networked, and mainly I reduced it, apologies, transferring strings. A lot of them were baked into the device, but some of them were also dynamically created by some measurement sensor values the device collected. But a lot were static. So they had this class fixed string. I figured out it's a class template which grades you based on this template parameter size tn, a car array of size n internally. It stores the currently stored number of characters in the string in m size. We might end up getting that in 26 as well in a different shape. It's default constructible. You can construct it with a constcar star. It obtains the size, copies the data over into the local buffer, and it has a member function size, data, and a lot more member functions in reality, but let's reduce this to that. They had this utility long before I came in, and they started like you see down in line 24 with the variable x. They told the developers, well, here is this fixed string class. Please use it to store your static strings or the strings that are limited or all the strings, whatever it was. It turned out that we developers are not too eager to count characters in a string. Might be different for you, but most people I met, they're not really interested in doing that when it comes to programming. So a lot of them said, yeah, 48 bytes, 128, that should be sufficient for my string, right? So they constantly over allocated, as I'm showing you here in X, where I have allocated 50 bytes for a way shorter string. This was realized, so they added a function, a make fixed string function that uses this template trick to obtain the number of characters of a car star literal, and use that constant to create a perfectly trimmed fixed string as I do it in Y. So that one is perfectly adjusted. All right, so When I came in, I saw this and I started asking, why not make it Constexpr? Oh, should be creating to Constexpr. And boy, I was told, no. Doesn't make sense, doesn't help. Because, and I preserved that, if you look at lines 24 and 25, there's things were already const, there's things were already static. So Constexpr, I've been told, will not do a thing. All right. Honestly, it took a lot of the budget to get approval to try out making that thing Constexpr. Took a longer time to get the permission than actually doing the change. And what I'm showing you here now is the code from the slide with a slight modification. You can see the uppercase Constexpr here. Uppercase Constexpr, well, indicates it's a macro, right? Because I have two different compilers running here. The one run you see in the middle defines Constexpr to nothing, while the one on the right defines Constexpr, as you can see it here, to the keyword Constexpr. Right, so we have the two concurrent ones. They both use a recent version of Clang. And if I check the original implementation, we go home with 209 lines of assembly. It's not correct. Compiler Explorer inserts a couple of blank lines, but let's work with that. 209. The code I have here is creating the two strings that you saw on the slide and printing that one out. Feels a little much for me, 209, but well, let's go with it. My Constexpr version, that one has, 78. So that's nearly a third of the original implementation. All I did was adding 6 times Constexpr. It might be more in the real world code base, of course, but I only added Constexpr. 1/3. That's not bad, right? But it's O0 if you check it close. So that's not fair, right? Let's use O3. Most people don't use O0 in their release builds. 42 lines. Okay, people weren't that wrong, right? Code didn't suck that much. 42 lines. The Constexpr version, oh look, it nearly fits on the screen. It has 31 lines. So it's only 11 line difference. Still a difference, a good one, but not that much anymore. But let me tell you, it's not really about the lines of assembly that differ here. Oh, no, maybe it is. It is, right? These here are these 11 lines of assembly, and I don't expect you to read it, not even that quickly here. I'm more into ARM assembly. This is x86 assembly. But what I can tell you about this is there are a lot of memos in there. And what this entire assembly function does is it runs for all your global static objects that require a constructor call. And they execute that one. And what's happening in there is all the fixed string objects like X and Y get created before main starts, but still at runtime. They occupy the storage space like 50, as I declared it for one of the fixed strings. And then they copy all the data from the ROM to the RAM into this data structure. So here is already the string I want, and that one now gets copied at runtime, and the very first thing from the ROM to the RAM. So this is how you can waste a lot of RAM, because you store strings twice. And you also pay with it with time, because the copying here, the creation, that costs time. This code isn't present in the Constexpr version. This is the main difference. This is not just the 11-line difference. This is a stack occupation and time-consuming difference more than the 11 lines itself. And it's so beautiful, the Constexpr version. If you look at this is what Clang understands from my object. It understands now that X is an object that resists in the ROM. It has the first field, 22, so that's the actual length of my string, followed by padding because the developer overallocated, followed by another padding because the fixed string itself is not properly aligned. For Y here, we see it slightly different, 25 characters stored in this string and only one padding required for the fixed string itself. So claiming the right version understands correctly how this object is laid out here. That's wonderful. That's perfect. This is the code I want. So this is the best example I can give you what Constexpr can do to your code. So it saves a lot space and time. You rarely get savings in both at the same time with just one action. It's brilliant. I really, really like that. I hope you appreciate it. What else do we have? Talking about being efficient. You might have heard about the std initializer list, right? It came in with C++11. We occasionally use it. So here's a usage. You shouldn't do that at home, right? But I declare a std initializer list on the stack and then use that one to pass it to a function called receive. Std initializer list of type int has a couple of values in it. If you explore what's happening here behind the scenes using C++ and sites, once again, there's a transformation that's called transform std initializer list. If I hit transform here and do the transformation, we can see these two lines come from the std initializer list. So what a compiler does here, whenever it sees a std initializer list, it creates an array in the background, the so-called backing array. That one is of the same type as the std initializer list. The size is equal to the number of elements in the std initializer list, and all the elements that we pass to the std initializer list, they get copy constructed into this array on the stack. The thing is const, and my std initializer list, my actual initializer list, takes a pointer to this array and the number of elements, so the size. This is a magic thing that always happens when the compiler sees a std initializer list. Okay, so much for the background, that we are all on the same page, what's happening behind a std initializer list. Now let's get rid of the std initializer list for a moment and use a initializer list free version, but an equivalent using a array, a C-style array. So I have here in my function receive that now takes a array of type int of size 4. That's a little lie. Look at the note below. And in fun, I'm creating then a array of type int of size 4, put the numbers in as before, and call receive instead. So this is our minimal version. If you use that and look at it in Compiler Explorer, we can see, well, yeah, this is the resulting assembly code. Here are the numbers we are storing in this initializer list on the stack, in the RAM. And then if you look at fun, we can see something similar that we saw before. Compiler is reserving stack space, the compiler is doing mem moves. So what's happening here is all the values that are perfectly in my ROM get at runtime, whenever we invoke fun, copied to stack space within fun. So we once again pay with time and memory. Can we change that? Can we do better? Well, for this particular code, we could say, let's make this array static, right? Because we know all the initializers are known at compile time. They never change. So it's const anyway. So we can make it a static variable within this function. Does that change things? Let's have a look. This here is the static version. This is shorter than the previous one, way shorter, because the implementation of fun here is shorter. We still have all the values in the ROM, but now fun, because it's static, fun is able to simply use a pointer to the ROM here and pass it to receive. It's const, receive cannot change it. The data is static, so we can directly access it. Once again, it's a similar pattern like the Constexpr. So this is really efficient working with your data. All right, you might now say, Andreas, nice we have this chat, but how does it help me with my std initializer list, right? Because in my std initializer list, if I make that one either static or const or both, it doesn't do its thing, because the backing array in the background, we don't control. It's the compiler that creates it. That's true. But we have the same case here. So the case we have is equivalent to the array case. My std initializer list has only initializers that are known at compile time. The list in the background would be const, so that thing is never changed. The code that you see here, that's the previous one, right? 24 lines of assembly compared to the 15, the previous version, used with static. And we can see all the copies here. I'm using currently GCC 13.3. And there is a very specific reason. It's C++ 17 and 03. If I switch the compiler, and I'm running a local instance of Compile Explorer, that's why I only have a few of them. If I switch to GCC 14.2, I'm not switching the standard, I'm not switching anything else. Down. So this version is a good portion shorter than the previous one. And once again, it's not just the lines of assembly, it's also the stack space that gets allocated. It's also the time you spend copying your data. That one here, once again, can simply use the pointer and the number of elements, create an initializer list, and pass it to receiver. And you're done. Why is that here in GCC 14.2? Because they implemented a C++26 change, a defect report against the standard, a DR, and that means they can retroactively apply it to older standards. So we fixed something in C++26, but it's applicable to previous standards. This is why if I simply switch the compiler to GCC 14, not changing the standard, I have an effect here. And GCC is the only compiler that implemented that change, and it follows the exact rules that I just explained using the regular C array. So if all the initializers are constants and known at compile time, the compiler is allowed to play this trick to make the backing array in the background static, like I showed you with the hand-rolled array version. And this is what saves you precious instructions here and time and stack space. So maybe you might not have the option to switch to C++ 2023, but maybe you have the option to update your compiler. That's a hard thing to do as well, but maybe that's just one step at a time. And that could give you better code generation for std initializer lists. As far as I know, GCC is the only compiler that implemented that so far, but the others will for sure catch up once they are starting implementing stuff for C++26 or completing their list. All right, excellent. So I hope you enjoyed the talk. I hope I could teach you something. This is part of a class I developed especially for teaching C++ to embedded developers, focusing on the needs there. If you like it, just hit the thumbs up button in YouTube or contact me if you want to have an in-house training. If you have questions because you're here in a virtual person at least, then please, now it's the time to move on to GetterTown, because there I will answer all your questions, at least until we run out. All that's left to say from me now here is thank you for watching, support CPP online, and I hope you have a great time there. And I'm Fertig.